So today we're going to be taking a look at the change of base law and how to use them to solve exponential equations. So the change of base law looks something like this. We have log base b of a, and we want to change it into a different form so that we can evaluate it. For example, if I had log base 2 of 8, I could write this as log base 2 of 2 cubed, and I could evaluate it. But if I had log base 2 of 7, well, we can't really do that because I can't write 7 as a power of 2 yet. And that's where the change of base law comes in. So if I let log base b of a is equal to m, in exponential form we get b to the power of m is equal to a. I'm going to log base x both sides. So what I'm doing here is I'm changing my base where we want to pick a base, both sides, there we go. We want to pick a base that would work. And so my x value has to be greater than 0 and my x value can't be 1. I can choose any other base I want. And what I get is log base x of b to the power of m is equal to log base x of a. Now this exponent, as we learned with that other rule, comes down in front and I get m times log base x of b is equal to log base x of a. And therefore, if I divide both sides by log base x of b, and I get the m by itself, I get this little guy over here. So what that tells me is something called the change of base law. And what this does is it literally changes the base into what you want it to be. Okay, so here's my change of base law. It says that if you have log base b, b on the bottom, b for bottom, log base b of a, you can change it to whatever you want it to be, whatever base you want it to be on the top, and that same base of the value on the bottom. So this is a very useful thing if the base doesn't turn out to be what you want it to be. So for example, if I wanted to find the value of log base 2 of 7 like I did before, I would have to see that it would be some kind of calculator like decimal type question. Because I know that log base 2 of 4 is log base 2 of 2 squared, log base 2 of 2 squared, which is 2, out pops the exponents. And I know that log base 2 of 8 is log base 2 of 2 cubed, out pops the exponent. That means that log base 2 of 7 is somewhere in between there. It has to be some decimal value between 2 and 3. And the decimal value means that we are now using our calculator. So to use our calculator, we have to recognize that our calculator only works in base 10. That's our log button. Or base E, that's our natural log button. And it really doesn't matter which one you use when you're going through this. You can use the log button or you can use the natural log button. Oops, just looking for my calculator. Here we go. And so if I wanted to evaluate log base 2 of 7, I can choose to go log base 10 of 7, that's the top value, divided by log base 10 of 2. I'm choosing to change the base to base 10. And then my base, this number here, is on the bottom. So really in my calculator what I would do is I would enter log 7 divided by log 2 and I would get this decimal value. So just checking it out, log 7 divided by log 2 on my calculator, I would get that equal to 2.807. What that really means is that if I'm evaluating log base 2 of 7, this means that I've got log base 2 of 2 to the power of 2.807 approximately, which equals 2.807. So that means that 7 can be written as 2 to the power of 2.807. Not that you'd really want to do that, but that's essentially what we're doing here. But this is how we evaluate this number. Notice that if you had used natural log button instead and gone the natural log of 7 divided by the natural log of 2, you still get 2.807. So this is a nice way of evaluating that type of number. You can also use it for, obviously, log base 2 of 8. If you tried log base 2 of 8, you'd go log of 8 divided by log of 2, and you'd end up with 3. So that's why your quiz is non-calculator, so you know your log properties. And now the second part of the class, these exponential equations will be with calculator. Okay, so let's take a look then at how else we can use the change of base law. We might be also able to use it like this. Write as a single logarithm. So if I write this as a single logarithm, I'm going to have 3 log base 4 of x plus 2 log base 8 of x. Now the thing that's really kicking this off right away is noticing that the bases are different. And because they are different, there's no way that we can do logs unless the bases are the same. So what I'm going to do is I'm going to change the base into something. And I'm going to change the base, so something that they have in common, I'm going to change it to base 2. So I'm going to get 3 times. If I want to change this to base 2 right here, I'm going to get log base 2 of x divided by log base 2 of 4. Then for my next one, I've got the 2 in front. And when I change this one, it's going to be log base 2 of x divided by log base 2 of 8. Let's go through and evaluate some stuff. So I've got 3 on the outside, I've got log base 2 of x, and in the denominator I want to evaluate log base 2 of 4. This is log base 2 of 2 squared. Out pops the 2. The next one is going to be 2 times log base 2 of x divided by log base 2 of 8. So log base 2 of 8, log base 2 of 2 cubed, out pops the 3. So what I've got is 3 over 2 log base 2 of x plus 2/3 log base 2 of x. And there's a bunch of different ways that you can do this. So you can either do this, log base 2 of x to the power of 3 over 2, bring those exponents up, x to the power of 2/3, and then multiply them together. That plus in the middle means that we're going to go log base 2 of x to the power of 3 over 2 times x to the power of 2/3. And then we add our exponents and get x to the power of, what is that? 9 plus 4 is 13 over 6. Get yourself a common denominator. And that's what it would look like all in one term. The other thing that you could do is you could think of this as like 3 over 2 log base 2 of x, and then 2 over 3 log base 2 of x, and we're collecting our log base 2 of x's. So I would get a common denominator, which is 6, times the top and the bottom here by 3, and I would get 9 log base 2 of x's. I would times the top and the bottom here by 2, and I would get 4 log base 2 of x's. So overall, I'm going to get 13 over 6 log base 2 of x's, and then I could bring that exponent up and I would still end up with that 13 over 6. Whatever sort of makes more sense to you, I think we can do that. All right, now what we want to do is we want to use our change of base law and our calculators to be able to solve exponential equations. So in the last class, we solved log equations. And when we did log equations, one of the methods was to change it to exponent form. With this one, with exponential equations, we're going to use logs for some of them. So if you remember, we had equations that looked like this before. We had something like 8 to the power of 2x minus 3 equals 4 to the power of 5 minus x. And these were ones that we saw like in grade 10. And they were fairly easy because what you could do is you could get a common base for these. The common base was 2, so I'd write this as 2 cubed to the power of 2x minus 3. 4 is 2 squared to the power of 5 minus x. I've got an inside and an outside exponent that looks like this. And so we get 2 to the power of 6x minus 9 and 2 to the power of 10 minus 2x. So 6x minus 9 is equal to 10 minus 2x. Bring all my x's together, bring the 9 across, we're going to get 19, and x is equal to 19 over 8. Which seems okay. I mean, it's a nice enough number or whatever. But here's the issue. I change one of these numbers and we've got ourselves a big problem. I've got 8 to the power of 2x minus 3 is equal to 5 to the power of 5 minus x. So now, because there is no common base, we have to go through a process that we use to solve any type of equations. Now, some of these are easier than others, and some you can have different forms where you can change to log form and so on. But changing to log form in this case is not that easy because you've got exponents on the left side as well as on the right side. So here is the process for doing this type of question. You are going to log both sides. And this is why I've been doing all these proofs with you so that you can see that we can just log both sides. Because we're going to use our calculator, use base 10 or base E. Okay, and it's up to you whether you want to use log or natural log for these. It makes no difference. So I'm going to use base 10 because I like to write the word log here. So log of 8 to the power of 2x minus 3 is equal to log of 5 to the power of 5 minus x. The reason why we log both sides is so that this exponent right here no longer has to float on the top. It can be moved to the front. And this exponent right here can no longer be moved to in the top here. It has to be moved to the front. Excuse me. So the reason why we log both sides is specifically to move that exponent to the front side. So we get log of 8. Now I'm going to do this guy, 5 minus x times log of 5. Okay, so log, what we did here was we bring the exponent down. So that's what we did there. We are then going to, and this is what I usually use. Oh, make sure in here that you use brackets. If you don't use brackets, these things can get very, very messy. So please make sure that you're using brackets when you're bringing this down. Brackets around the 2x minus 3 and brackets around the 5 minus x. Because what we're going to do next is we're going to distribute the logs. Please don't put this in your calculator yet. There are so many places where you can get rounding errors. So we're going to get log 8 times 2x and log 8 times negative 3 and log 5 times 5 and log 5 times negative x. This is what it's going to look like. 2 times log 8 times x minus 3 times log 8 equals 5 times log 5 minus log 5 times x. Okay, so that's log 5 times x. We are going to solve for x. And to solve for x, bring all the terms with x to one side, everything else to the other side. So that means that I'm going to keep this guy over here and I'm going to bring that guy over. So I'm going to add log 5 times x to both sides. So I get 2 log 8 times x plus log 5 times x. So these are just numbers that are in front of my x's, equals, and then I want this guy here to go to the other side. So if I want that guy to go to the other side, I've got 3 log 8 plus 5 log 5. Now, to collect on my x's, what we're going to do is we're going to factor out the x. And if I factor out the x, I've got 2 log 8 and then log 5 and equals to 3 log 8, I'll put a little dot there, plus 5 log 5. And then I'm going to divide to be able to isolate for x. So I'm going to divide both sides by 2 log 8 plus log 5, and I'm going to get x equals to 3 log 8 plus 5 log 5 divided by 2 log 8 plus log 5. This is what is referred to as your exact value. So if you go off to university or whatever and you don't get a calculator, which is very often the case, you want to be very careful. So that's going to be your exact value. One of the biggest challenges we have is to try to get an approximate value from that from your calculator. So you have to make sure that you and your calculator are thinking in the same sort of brain pattern. So try to get your calculator out and find the approximate solution. Remember to 3 decimal places. So pause this video if you want, or whatever it is that you need to do. but get your calculator out and try and make sure that you can get an answer of 2.477. That is your approximate answer for this one. If you can't get 2.477, have someone help you to figure out how your calculator works. Start using lots of brackets. Brackets are very, very good. So we want to make sure that you can do that. Okay, I'm going to do one more example, and this is considered to be the difficult example. So here we are going to solve 5 times 2 to the power of 3x plus 1 is equal to, I don't want to do 2. Let's do 3 to the power of x plus, I'll do 2x plus 1. So what we're going to do is we're going to follow our steps. We're going to log both sides. So log of 5 times 2 to the power of 3x plus 1 is equal to log of 3 to the power of 2x plus 1. Feel free to use natural log if you want to. Right over here, dun dun dun, I'm going to show you what the fatal error is. Here is the fatal error. We can't really do much more from this. The fatal error is to bring the 3x plus 1 down in front at this point of log of 5 times 2 equals to the 2x plus 1 and log of 3. And the reason why this is a fatal error is because this exponent right here that you've brought down now works on both the 5 and the 2, which it didn't before. This exponent right here actually only comes from the 2. So what we actually have to do is we have to see that there's a multiplication sign in here. And multiplication in logs really means that we're going log of 5 plus log of 2 to the power of 3x plus 1. You have to separate those guys first before you can start dealing with those exponents. Okay, now I'm going to start bringing everything down. So my exponent now is going to move, and this exponent is going to move. You are going to use brackets, right? And so we're going to get 3x plus 1 times log of 2 and 2x plus 1 times log of 3. Distribute, 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 distribute. Log of 5 plus 3 log of 2 times x plus log of 2 is equal to 2 log of 3 times x plus log of 3. Remember, we are trying to collect all of your values for x. There they are. Bring them over to one side. Bring everything else over to the other side. So we have 3 log of 2 times x minus 2 log of 3 times x. That's one side. And then I got to get this guy, and this guy over on the other side. Excuse me. We've got log of 3 minus log of 2 minus log of 5. Factor out the x. 3 log of 2 minus 2 log of 3 equals to log of 3 minus log of 2 minus log of 5. And then finally, x is equal to log of 3 minus log of 2 minus log of 5 divided by 3 log of 2 minus 2 log of 3. Again, that is your exact value. That's the safe value. If you put this into your calculator, and make sure you try it so that you're not surprised, right, later on, make sure you and your calculator are thinking the same way, you should end up with approximately 10.222. Okay, so you guys are going to go practice some questions. Hopefully this makes sense. And yeah, good luck with everything and see you later.